Okay, now then at least you have started doing some work on statistical mechanics. Do you have any questions about the homework questions? Question? Okay. Now today we will be starting grand canonical ensemble. You see, we had started from the microcanonical. In which we basically assume that our system is isolated. So that n is constant, E is constant. Then we continued and we studied the canonical ensemble. Which is, in this system, n is constant, but E is not constant. A typical system with these properties is a system in contact with a heat bath. With a reservoir. And in the microcanonical ensemble, our basic assumption was that all the states are equally probable. So if there are omega E states, all of them are equally probable, and we had defined the entropy of the system to be k times logarithm of this omega, which was the number of states. Now in the canonical ensemble, for our system, we didn't assume that all states are equally probable, but the probability of a state of the state R, probability for my system to be in a microstate R was given by e to power minus beta ER being the energy of my the microstate divided by some normalization. Let's say in your book is Q. And the Helmholtz free energy was expressed in terms of this function Q as minus KT logarithm of Q. And this beta parameter is just 1 over KT. And once we have the probability distribution, we can basically calculate everything. And the important thermodynamic relation with the Helmholtz free energy, remember A is just E minus Ts or U minus Ts, and dA is equal to minus SDT minus PdV plus mu dN. So from these information, once you calculate Q, you practically can calculate everything. All the thermodynamic properties of the system can be calculated. Well, the next step would be just to say, well, in the canonical E is not constant, but N is still constant. The grand canonical ensemble N also is not a constant. So such a system is a system which is in contact with both a heat and a particle reservoir. You see, when we are talking about systems, most of the time we draw these rectangles, but I mean, our systems need not be separated by such a physical boundaries. You see, you can just imagine the particles in that corner of this classroom. So there's no boundary separating that corner with the rest of the classroom. So the particles in the atmosphere in this classroom, they can just exchange, or you can just imagine this mathematical region bounded by my hands. So the particles can get in between my hands or just leave that. So the number of particles inside this region will not be constant. So such a system we can treat in this grand canonical ensemble. Now, again, we will be asking more or less the same question in the case of the canonical ensemble. You see, in the canonical ensemble, the first thing we asked was, what is the probability that my system will be in a microstate with a given energy? That was what that PR is. Now, in the grand canonical ensemble, we will be asking the question, what is the probability that the system has ns particles and is in a microstate of these ns particles with energy ER. So what is this probability? So since the number is also constantly changing, of course we will still have some constraints. On the average, the system will have some kind of an average energy, which we can write as PRS times ER, sum over all microstates, or all possible values of R and S. And there will be an average number of particles. These should be fixed. Given these constraints, what is the probability distribution? Again, as in the canonical case, that we can make several approaches to calculate this probability. One is just to use the microcanonical ensemble, the concepts of the microcanonical ensemble. You see, this is my system. Let's say this is my system in contact with a heat reservoir and the particle reservoir. But if I imagine the whole system, my system plus the heat and the particle reservoirs, this is an isolated system. So for this system, I can use the microcanonical ensemble. So let's say this has energy ER and the number of particles NS. Let's say the reservoir has energy ER prime, number of particles NS prime when my system has the energy ER and the number of particles NS. So let's just call the E0 to be the total energy, and N0 to be the total number of particles. So the probability that I am looking for, well, first of all, is the number of microstates of the combined system in which my subsystem, the system that I'm interested in, is in this state that I'm interested in. So that's the probability we are looking for. Now the probability is number of outcomes that you want divided by the total number of outcomes. Well, the total number of microstates is of the whole system, we denote it by omega, let's say T, meaning that for the total system of E0, N0. This is the total number of outcomes. The outcomes that I want is just, well, the system that I'm interested in should be in one particular state, given number of particles and energy. So there's 1 times, well, I don't really care what the microstate of the reservoir is. So if I multiply this 1 by the number of microstates that the reservoir can be in such that it will have the energy ER prime and NS prime, well, this is the probability I'm looking for. Do you agree?
I didn't get why did you choose omega r instead of you. This is the number of states of the reservoir, right?
Well, you see, the denominator is the number of states of the whole system.
Mm-hmm.
Omega r is the number of states of the reservoir only. Because you see, that 1 over there is the number of microstates that my system can be in. Because when I'm defining this probability, I'm saying that I'm asking for the probability for the system that I'm interested in to be in one particular microstate. It's not the only microstate that has this energy and that number of particles, but I'm only interested in the system that I'm interested to be in that particular one. So that's why I have that 1. Well, the denominator is just a normalization constant, so this probability up to normalization is basically the number of microstates that my reservoir can be having energy E0 minus ER and N0 minus NS. Because the total number is fixed, total energy is fixed, ER and S are the energy and the number of particles in the system that I'm interested in. What remains is the total energy and the number of particles of the reservoir. Now, rather than, this ER, since the reservoir is, by definition, they are huge, ER over E0 and NS over N0, these numbers are much less than 1. So I will be basically making a Taylor expansion, just like as I did in the canonical ensemble. You see, in the canonical ensemble, the only difference in this derivation is that in the canonical ensemble, the number was fixed. So I just ignore the argument n. Well, logarithm of omega r is just logarithm of omega r for the values E0 and N0 plus derivative of the logarithm of omega r with respect to E evaluated at E0 multiplied with minus ER plus derivative of the logarithm of omega r with respect to N evaluated at N0 multiplied with minus NS. Now keep in mind that logarithm of omega r is nothing but minus the entropy of the reservoir, plus the entropy of the reservoir divided by K. So the derivative of the logarithm of omega r with respect to E with constant number of particles is equal to derivative of S, the entropy of the reservoir with respect to E at constant number of particles divided by K, but this is nothing but how we define the temperature. Okay, it's the temperature of the reservoir, but since we are assuming that the system is in equilibrium with the reservoir, it's the temperature of my system also. So this is 1 over kT. Well, similarly, the derivative of the logarithm of omega r with respect to N with energy fixed, this is 1 over K, derivative of the entropy of the reservoir with respect to N with energy fixed. And again, this derivative is just mu over T. T is the common temperature, and mu is actually the chemical potential of the reservoir, but when we were discussing thermodynamics, we had seen that if there are particle exchanges, the chemical potentials of the systems exchanging particle are equal in equilibrium. So this mu is the chemical potential of the reservoir, but also of my system. So this is mu over kT, which tells me that omega of the reservoir at energy E0 minus ER and number of particles in 0 minus ns is some constant that doesn't depend on ER and ns times e to the power minus, if you look at this expansion, the first term, this is 1 over kT, and this is mu over kT. So that derivative is minus mu over kT. E to the power minus this minus over here, 1 over kT times ER minus mu times ns. This is the number of particles, number of microstates of the reservoir. Well, the probability, we had already said that it's proportional to omega r E0 minus ER N0 minus NS, which is proportional to e to the power minus 1 over kT ER minus mu NS. Or putting in the proportionality constant, the probability that we are looking for is e to the power minus, let me put the beta, so this is the probability we are looking for. So I repeat, this is the probability for my system that is in contact, in equilibrium with heat and particle reservoir. The probability that it will be in a particular microstate, in one of the possible microstates, that has an energy ER and the number of particles ms. Well, what is beta? What is mu? Well, we just fix them through our constraints. So remember what was our constraints. We have the average number, which is just NR PRS, average energy, which we also use the symbol U for. This is ES, no, this is NS ER. So these two equations determine beta and beta mu, or mu. So we choose them such that these equations are satisfied. Now let's say this Q this sum. This is the grand canonical partition function. Now, quite often we define some other quantity, let's call Z, as e to the power beta mu. This is called the fugacity. But mu is kind of an unknown that needs to be determined. Instead of mu, you can just use the Z as your unknown. Now, in terms of this parameter, this Q, the grand canonical partition function is Z to the power n e to the power minus beta ER. And keep in mind that we are here summing over all possible microstates with all possible number of particles and all possible energies. Well, since we have these two different kinds of sums, one over all, for a given n, we are summing over all possible microstates with different energies. And then we are summing over n. We can just separate those two sums. But if we make such a separation, this is just sum over s, or the number of particles, z to the n, ns, sum over r e to the power minus beta er. But the second sum is nothing but the canonical partition function for a given number of particles. So this grand canonical partition function, you can evaluate it if you know the canonical partition functions through such a relation. Of course, this wouldn't be so much interesting most of the time, because if you can calculate the canonical partition function, then you can study the system anyway, without referring to the grand canonical partition function. But in some cases, it's not so easy to evaluate the canonical partition function, but there are other means of evaluating the grand canonical partition function. So especially when these quantum mechanical effects will be important, we will see some cases. Now, this depends, of course, on this grand canonical partition function depends on the temperature. Now, let me write somewhere else. It depends on temperature. Well, there's a beta dependence. Beta is just the inverse temperature. It depends on mu, or z, if you like. Z is just a function of temperature and mu. And it also depends on the volume. Volume, because this canonical partition function depends on the volume through the allowed possible energy eigenvalues. Okay, so this basically allows us to calculate the probabilities, and once we have the probabilities, we can basically calculate whatever you like. Now, of course, the next question would be, okay, we can calculate whatever we want, but what is the relation to thermodynamic quantities? Now, if you remember, in the case of the canonical ensemble, we calculated the partition function, and the logarithm of the partition function was nothing but the minus beta times the Helmholtz free energy. And then, once we know the Helmholtz free energy, we can calculate everything from that information. Well, we will look for a similar thing over here. Well, there's some derivation in your book, but let me just present an alternative way of relating this Q to the thermodynamic quantities. Let's look at the entropy. You see, we had defined the entropy in the canonical ensemble as sum over the probabilities times the logarithm of the probabilities, with a minus sign, or if you like, we could write this as average of logarithm of PR with a minus sign, or logarithm of the probability of inverse probabilities, the average. This is the entropy. Now, this is in fact the entropy whatever your system is. Canonical, grand canonical, or you can even use this to measure the information in your system. In information theory, this definition of entropy is also used. So let's use this one. We already know the probabilities. So in the canonical and grand canonical ensemble, the entropy will be just the average of, well, let me add the minus 1 logarithm of the probabilities. Well, the probabilities is e to the power minus beta er minus mu n divided by this q. Or let's say this is equal to minus average of minus beta ER minus mu NS minus the logarithm of this cube average, which is equal to, well, let me just multiply out the minus signs, and I have beta u minus mu beta n. These are the averages. And then I have the average of logarithm of q, but keep in mind q is just a number, a normalization constant. So its average is just itself. So this tells me that the logarithm of q, this grand canonical partition function is equal to s minus beta u minus mu beta n. Let me take the beta out. S over beta, sorry, this is plus u minus mu n. So let me make one correction. The entropy is not this one. This is S over K. Or this is equal to beta Ts plus u minus mu n bar. Okay, let me correct the signs. Okay, this is plus, this is minus I have over here. This is plus, this is minus. This is plus, or the logarithm of q is equal to minus beta u minus Ts minus mu n. So let's see what this is. Let's remember thermodynamics. du was equal to s dt minus p dv plus mu dn. So du minus Ts minus mu n would be just minus, no, this is TDS, sorry. Minus S dt minus P dV minus N d mu. So d of minus kt logarithm of q whatever that is would be minus s dt minus p dv minus n d mu. Now this is in your book, it's also called the q potential, small q. Let me just rewrite it once more. Now the q Q is defined as minus beta U minus TS minus mu and bar also. Q is an extensive property, meaning that if you double your system, it's doubled. Because U is an extensive property, S is an extensive property, N is an extensive property, whereas the temperature and mu are intensive properties, and also the pressure is positive here over there. But on the other hand, Q, if you look at this expression over here, Q can be written as, or KT times Q can be written as a function of temperature, volume, and the chemical potential. If you look at the arguments of Q, the only quantity that is extensive over there is V. So this has to be proportional to the volume, because if you try to imagine any function, that should have the property that when you double the v, the function should also be doubled. So it has to be proportional to v. With a proportionality constant that depends on temperature and the chemical potential only. That proportionality constant cannot depend on V. Again, the reason is if you just multiply V by some constant, Q should be multiplied by exactly the same constant. Now the next thing, what is that F? Well, let's see. If you look at this relationship over there, I can write the pressure as the derivative of KTQ with respect to V at constant temperature and chemical potential, which is KT times the derivative of Q with respect to volume at constant temperature and chemical potential. Well, I know the general form of Q, just the previous line. So this is KT times F. So which basically tells me that F is nothing but P over KT. Whatever the system is. Usually up to this point I'm not making any assumption of any sort. For an arbitrary system this should be true. And so Q, there's a minus sign over here, and hence over here. So Q is nothing but PV over KT. Or, if you like, PV is KT times minus KT times this Q potential, or minus KT times logarithm of the grand canonical partition function. And once you know this grand canonical partition function, you can basically treat this thing as one of the thermodynamic potentials. And then you can calculate obtain the entropy. The pressure is already given by the partition function, and the number of particles. So everything is known. Let's do some examples. Some examples that we had already discussed to some extent. like the ideal gas. Well, the grand canonical partition function, we had already seen that this is just sum over all the number of particles times fugacity to the power n times the canonical partition function corresponding to n particles. But the canonical partition corresponding to n particles for the ideal gas, well, ideal gas meaning that the particles making my gas are not really interacting with each other. The particles making my gas can still be molecules, non-interacting molecules. And the partition function for such a system, the canonical partition function, can be written in terms of the partition function for a single one raised to the power n. And if they are indistinguishable, so we should divide by n factorial, which is sum over n z times q1 to the power n divided by n factorial. So I know what my q is, the grand canonical partition function. This is equal to the exponential of z times q1. So the q potential is logarithm of q1 logarithm of q, not q1, which is just z times q1. Now q1, I can also make one more assumption. q1 will be a function of the volume and the temperature of the system. But if you count the number of particles making a system, number of microstates that a single particle can be in a volume V, that will be proportional to V. So this Q1 should be V times some function of T. Well, I'm using the same symbol F all the time, but that F, this F is not the F that I used before. It's a different F. So the Q is just now Z times V times F. And keep in mind that this F is a function of temperature only. So, well, we know that Q is minus PV over KT. So this tells me that PV for the ideal gas, I can also write it as minus KT times Z times V times F. What about the number of particles? The average number of particles. Well, N, we said that this we can write as NS times PRS, or sum over NS e to power minus beta E R minus mu NS divided by the grand canonical partition function, which we can write as 1 over the grand canonical partition function times the derivative with respect to alpha of e to the power minus beta ER plus alpha NS, evaluated that alpha is equal to beta mu. Well, of course, this derivative with respect to alpha when beta is constant, or temperature is constant. Or I can write the same thing as 1 over Q, derivative with respect to mu of this sum Well, when I take the derivative with respect to mu, it brings down this factor ns, but also it brings down this beta, so let me divide by beta. And again, this derivative is evaluated at constant temperature. So I can just take it out of the derivative with respect to mu. So n is 1 over beta times derivative with respect to mu of this Q function at constant temperature and volume. Well, volume dependence at constant volume comes from the fact that ER is not changing. ER, the volume dependence is only through the possible values of ER. Since when I'm taking the derivative with respect to mu, I'm just ignoring any changes in R, that derivative is at constant volume. Well, n is kT, derivative with respect to mu of Q. Well, Q we had already evaluated, minus kT ZVF. The volume times F at constant temperature and volume. So the number of particles is kT squared. If I didn't make some mistake in factors beta, is kT squared times V, since V is constant. F depends only on the temperature, and I'm taking the derivative with F, V constant. Derivative of Z, which is e to power beta mu, with respect to mu. Well, this is minus kT Vf Z, if you take the derivative. This is n, the number of particles in terms of the chemical potential, temperature, and the volume. Well, let's go back. We had evaluated PV. So this tells me that, oh, sorry, I might have missed some factors. When I take the derivative with respect to mu, it brings a factor beta. It cancels one of these kTs over there. So let's go back if I missed some factors somewhere. This is the average n. This one's 1 over q. I'm taking the derivative with respect to mu. That brings a factor beta ns. I don't want the beta, so I divide by beta. So this is the average number of particles. Derivative of q with respect to mu. So this is q. Q is kTZVF, correct? Oh, sorry. Q is not kTZVF. Q is ZVF. So when you take the derivative, there's no, there's just a single kT over here. Which is cancelled. So this is what we have. There's still one sign mistake we have. You see, if you look at over here, this is just n. So PV is n kT. If you correct that sign mistake also. So let's look for that sign mistake. So this is our logarithm of q, so it's beta ts, there's a minus beta over here. du is this one, du minus ts is just this one over there. u minus ts is minus kt logarithm of q. Oh, here there's this sign mistake. Here this is minus ktq. So there's no, okay, so there are these two. Derivative of minus ktq with respect to v is minus p. So you see derivative of minus ktq with respect to v gives me minus p. So there are two minuses over there. And hence I don't have a minus sign over here. This is plus. So here I have a plus. This is plus, here I have a plus. So I have a plus sign over here. So PV is equal to NKT. So just like in the canonical and the microcanonical ensemble. And then, of course, you can just go ahead and calculate the energy. Well, let's calculate U. U is the average energy, which was defined as ER times PRS, sum of ER e to power minus beta, E minus mu, N, divided by Q. So U is equal to, if I take the derivative of Q with respect to beta, well, you see, if I take the derivative with respect to beta, keeping mu fixed, I don't get beta mu n. I don't get E. I also get E minus mu n. So I should add to this mu and average. So this is U is equal to minus derivative with respect to beta of Q at constant mu and T, no, mu and V, plus mu and average, if you like. Now let's use what Q was. Q was just, you see, this is our Q. And we had also calculated the number of particles, VFZ, VZF of T. So let's calculate the derivative of Q with respect to beta. But that is derivative of Q with respect to temperature times T squared, like KT squared. This is equal to minus KT squared. If I take the derivative of Q with respect to T, I get KZVF plus KTZVF prime. This is equal to minus KT squared ZVF minus KT squared times TZVF prime. And just substitute back both this derivative and the n, you get U. let's assume a simplification. Let's assume f of t is just t to the powers t to the some power n. It's proportional to. In some simple, in the ideal gas that we had studied, this was actually indeed the case. So that f prime is just n times f. So this is the simplification I will get. So dq by d beta at constant v and mu is minus kt squared zvf minus kt, no sorry, n over t minus kt squared tzv n over t times f. So these t's will cancel, and I have kt squared in both terms, z times v times f in both terms, and then I have minus in both terms n plus 1. So u is, if you go back, is minus this derivative plus mu n bar, mu vzf. No, sorry, u is, no, mu n bar is. Now basically you can do whatever you want from this point on. Any questions? Let's give a break here, and then we will continue next hour.